everyone! In this video we're going to start chapter 5, which is an introduction to chemical reactions. So off to the side I have a picture of different types of batteries, and within batteries we see chemical reactions, and these chemical reactions release energy which we can use to power our devices. So the first thing that we need to understand before we dive into chemical reactions is something called the law of conservation of matter. Sometimes this is called the law of conservation of mass instead of matter, but this is a law, and in science, a law is a general statement that explains a large number of observations. So this kind of goes back to the scientific method. We make a lot of observations, and then we come up with a hypothesis, we test that hypothesis, and eventually, if we have enough evidence, we can create a law. So before being accepted, a law must be verified many times and under many different conditions. So the law of conservation of matter states that the amount of matter in a system is conserved. So what does that mean? Well, down below I have a reaction between methane gas, which has the formula CH4, and methane gas is also called natural gas. This is what powers gas stoves, for example. And if that reacts with oxygen, O2, one of our diatomic molecules, we form carbon dioxide and water, H2O. But notice that methane, CH4, has to react with two oxygen molecules. So we have two oxygen molecules up above, and then we produce one CO2 molecule and two water molecules. Now, the reason for that is, again, we have to conserve matter in a reaction. So the atoms on the left side of this reaction arrow have to match the atoms on the right side. Now, they can rearrange and form new things, but we have to have the same number of atoms in the reactants and the products. And that makes sense because we can't just randomly lose atoms or gain atoms. That wouldn't really fit with our conservation of matter. So another way of stating this law is, in a chemical reaction, matter is neither created nor destroyed. So for example, let's say that we were performing a reaction where mercuric oxide, HgO, breaks down or decomposes into mercury and oxygen. So this is not a balanced reaction, but we'll balance some reactions later. But the main idea here is, let's say we weigh out the mercuric oxide to start, and we find that our sample weighs 100 grams. Now, when it decomposes into mercury and oxygen, the mass of everything should still add up to 100 grams. So the amount of mercury we end up with is 92.6 grams, and the amount of oxygen is 7.4 grams. Now, if we add that together, we get 100 grams. So the mass on the left side of the reaction matches the mass on the right side of the reaction. So that's why sometimes this law is called the conservation of mass as well. Now let's step through chemical equations in a little more detail. I've showed you a couple of them, but let's just talk about what everything means in those chemical equations. So in general, chemical equations represent the process of a chemical reaction or change. So to simplify the way that we write reactions, we use formulas instead of names, and that way we can also keep track of atoms and where they're going. So down below I have that mercuric oxide again, and we used the chemical formula for mercuric oxide, which is HgO, much simpler to write. And then in parentheses next to that, we have a lowercase s. So S stands for solid. So not only can we tell somebody else which reactants we're using, but we can also tell them what phase the reactant is in. So in this case, the reactant is a solid. Next, we have our reaction arrow. So this is going to separate the reactants from the products. And then in the product side, which is past the arrow, we have our first product, mercury, which has the symbol Hg. And next to that, we have a lowercase l in parentheses. So L stands for liquid. So that tells us that mercury is in the liquid phase. Next to that, we do have a plus sign, so that is just separating the different products. But obviously, we could use that in the reactant side if we had multiple reactants. We could just use the plus sign to separate them. And then finally, we have oxygen, which is a gas. So that is given a lowercase g in parentheses. There is one other phase that you might see in reactions, and that is AQ, and that stands for aqueous. And aqueous means that it is dissolved in water. So later on, when we get into solution chemistry, we'll see aqueous more often because most likely we're dissolving our reactants in water, and then our products are forming in water as well. All right, so I mentioned earlier this equation is not balanced. We don't have the same number of atoms on the left and the right. So let's talk about how to balance chemical equations because we want to make sure we have the same number of atoms on both sides. So again, according to the law of conservation of matter, the number of atoms of each element in the reactants should equal the number of atoms of each element in the products. So let's look at this example down below. We have hydrogen gas, H2, and that is reacting with oxygen gas, O2, and the product is water, which is a liquid. I put little underline symbols here, here, and here because what we're going to do is we're going to add numbers in front of each reactant and product to balance the atoms. So essentially, we're going to multiply each reactant and product by a number so that we can make sure we have the same atoms on the left and the right. All right, so let's start. What I usually do, I make a table of reactants versus products. And then I list each of the elements that I have in the reaction on the left. So we do have hydrogen and oxygen, and that's it. Those are the only two elements in this reaction. So now I'm going to count how many hydrogen atoms I have on the left in the reactants. And it looks like I just have 2. So I'll put a 2 there. And then on the right-hand side in the products, I also have 2 hydrogens. So far so good. Hydrogen is balanced. Let's look at oxygen. So I have 2 oxygens in the reactants, and I only have 1 oxygen in the product. It doesn't have a subscript next to oxygen, so that tells me I only have 1 oxygen in the products. All right, so it looks like oxygen is not balanced. But I can very easily balance oxygen in the products by multiplying this entire H2O molecule by 2. So that means we have now also changed the number of hydrogens because we're going to multiply 2 by 2 for hydrogen. All right, and then we also multiply oxygen by 2. So we now have 4 hydrogens in the products and 2 oxygens in the products. Okay, so oxygen is now balanced. We have 2 oxygens on each side, but hydrogen is no longer balanced. We have 2 on the left and 4 on the right. So what could we put in front of H2 on the left in order to balance that? A 2. We'll just multiply it by 2. So that will give us 4 hydrogens on the left and on the right. Now that means that we did not have to touch O2. So we can leave that spot blank in front of O2, or we could write a 1 if we want to just keep track. But typically we just leave that spot blank, and that will tell the audience that we're relaying this information to that that is a 1. So now we have a ratio of 2 H2 molecules reacting with 1 O2 molecule to create 2 water molecules. And this will become important later when we start trying to figure out how many product molecules we might make or how many reactant molecules we need. So this slide is very wordy, but this does give a lot of tips for balancing equations. So first, we want to determine the correct chemical formulas for each reactant and product. So if we're not given the molecular formulas for each reactant and product, we'd have to write those ourselves. Most of the time, though, you'll be given the formulas. And then we write the skeleton equation. So we just put the bare minimum down. What are the reactants? What are the products? Then we're going to count the number of atoms of each element that appears as a reactant and as a product. So we can make that same table that we made earlier. And then, just like we did on the last slide, we're going to balance each element one at a time. And we'll do that by placing coefficients in front of the formulas. So again, essentially multiplying each molecule by a number. Now, one thing to note with that, we never change the subscripts in a chemical formula because that's going to change the molecule itself. You can only balance equations by using coefficients. So, for example, on the last slide, if we had written, let's say, H4 instead of H2, that would be a completely different molecule with different properties. So we cannot change the subscript. It has to stay the same molecule. All right, and then the next bullet point, check each atom to be sure that they are equal on both sides of the equation. So you just want to go through, make sure you have the same number of atoms on each side. And then, last but not least, make sure that all of the coefficients are in the lowest possible ratio. So for example, let's say we balanced everything and maybe we had a ratio of 4 to 2 to 2 to 4. That's not the lowest ratio possible because we can divide everything by 2. So it would actually be 2 to 1 to 1 to 2. So just take a second look at the end and make sure that everything's in the lowest ratio possible. All right, so let's balance the following chemical equation to get a little more practice. So I recommend trying this one on your own first. You can make a table of reactants versus products and then count each element on each side. And then see if you can figure out the ratios for each reactant and product. So pause the video, try it on your own, and then we'll go over it together. All right, so I'm going to make that same table that I made before. So reactants on the left and products on the right. Now in this reaction, we have a molecule C2H4 reacting with oxygen, and both of those are gases. And then they form carbon dioxide gas and water. So looking at the elements that I have here, there's carbon, hydrogen, and oxygen. Okay. So one thing I'm noticing, oxygen is in both of the products, which can make it a little challenging to balance. So I'm going to leave oxygen until the very end, and I'm going to balance carbon and hydrogen first. So we'll balance oxygen last, since it's divided between both products. Okay, let me use a different color here. So it looks like we have, oh, actually I'm going to use the same color. Looks like we have 2 carbons in the reactants and only 1 carbon in the products. We have 4 hydrogens in the reactants and 2 in the products. And we have 2 oxygens in the reactants, and we have 1, 2, 3 oxygens in the products. So that's a little tricky. All right, so let's start with carbon. What can we do to balance the carbon atoms? Well, we could multiply CO2 by 2. So that would change the number of carbons in the products to 2. But we're also changing the number of oxygens. Now, initially, we had 2 oxygens here, but we're going to multiply that by 2. So we have 4. And then we also have this other oxygen in the water molecule. So we actually have 5 now. Okay, so let's balance hydrogen next. So what do we need to do to balance hydrogen? Well, it looks like we need more hydrogens in the products, and we could just very easily multiply H2O by 2. So that will give us 4 hydrogens, but we're also changing the number of oxygens now as well. All right, so let's see, we've got 2 times 2 oxygens from CO2, so that's 4, plus now we have 2 oxygens in H2O. So 4 plus 2 gives us 6. All right. So that's going to be a lot easier to balance now. So what can we do to balance oxygen? Because we only have 2 oxygens in the reactants How can we get that to 6? Well, we can just multiply O2 by 3. So that will give us 6 oxygens. So let's just double check. We have 2 carbons on each side, 4 hydrogens on each side, and 6 oxygens on each side. So we are all set. This is a balanced equation, and we're following the law of conservation of matter. So we can see that there's a ratio of 1 to 3 to 2 to 2 between the reactants and the products. All right. Now, let's look at a slightly more difficult problem. What if we have a reaction equation that contains polyatomic ions? How do we balance that? So I don't recommend going atom by atom in this case. I recommend going ion by ion. So treat each polyatomic ion as one unit, and that'll make balancing a lot easier. So let's do this one together. So it looks like we have lead 2 nitrate, so remember nitrate has a -1 charge, and there's 2 nitrates there, so that must mean lead has a 2+ charge, or a +2 charge, whichever way you want to say it. That's reacting with sodium chloride, NaCl. So sodium has a +1 charge, chloride has a -1 charge. And then if we look at the products, everything's kind of swapped places. So now sodium is bonded to nitrate, and the charges are balanced there. And lead, which is +2, is now bonded to 2 chloride ions. So those are balanced as well. So this last set of molecules, ionic compounds, let's name these. So we have sodium nitrate and lead 2 chloride. So remember, lead is one of those ions that can have multiple charges. So we do have to list the charge in Roman numerals and in parentheses to indicate what the charge is. All right, anyway, let's write our little table, reactants versus products. And we have, let's see, a lead +2 ion, a nitrate ion, a sodium ion, and a chloride ion. All right, and then how many lead ions do we have in the reactant side? Just one. And how many lead ions do we have on the product side? Just one again. And then how many nitrate ions do we have on the reactant side? Well, we have a subscript of 2. So that means we have 2 nitrate ions. On the product side, though, we don't have parentheses around NO3. So that means we only have 1 nitrate ion. And then how many sodium ions do we have on the reactant side? Just 1. And it looks like we also just have 1 on the product side. And then the chloride ion, looks like we just have 1 on the reactant side, and we actually have 2 on the product side. Okay, so this will make it much easier to balance, because instead of trying to individually balance let's say the nitrogen atoms and the oxygen atoms that are in nitrate, we're just going to treat NO3 as an entire unit. It'll be much, much easier that way. So it looks like lead is already balanced, but the nitrate ion is not balanced. So what can we do to balance that? So we can just put a 2 in front of NaNO3, sodium nitrate, and that's actually going to change not only the amount of nitrate ions, but the amount of sodium ions. So now there's 2 of each in the products. So now we also need to balance the sodium ion. So it looks like we need to multiply sodium chloride by 2 to give us 2 sodium ions, but we're also now going to have 2 chloride ions on the left. But that's great because we needed 2 chloride ions. We already had 2 in the products, so now we have 2 in the reactants. All right, so it looks like we have a ratio of 1 to 2 to 2 to 1. All right, so again, with polyatomic ions, remember to treat the polyatomic ion as one unit. Don't separate it into atoms, and that will make it much, much easier to balance your equation. Now, this is going to lead us into something called stoichiometry. So a balanced chemical equation shows the numerical relationships between reactants and products, and that's by using coefficients. Now, the study of those relationships is called stoichiometry. So it's kind of a fancy word for ratio. Now, we can see this in not just chemistry, but in areas like cooking or baking, which is essentially chemistry, right? You're mixing things together and you're coming up with a new product. So, for example, let's look at a recipe for chocolate chip cookies on the right. Now, in order to make the chocolate chip cookies, we need 3/4 of a cup of butter, 3/4 of a cup of brown sugar, 2 eggs, 3/4 cup sugar, 2 teaspoons vanilla, etc., etc. So we need very defined ratios of each ingredient to make the chocolate chip cookies. And this should give us a certain amount of chocolate chip cookies. In fact, it should give us 24 chocolate chip cookies. So this is also stoichiometry. We're just looking at the ratio of our reactants or ingredients to the product. Now, what we can do with that, we can set up what are called conversion factors, or just ratios, to determine how many cookies or how much of the product we can make. So let's say we were just looking at butter related to cookies. We could say that we will make 24 chocolate chip cookies for every 3/4 cups of butter. So let's say we actually only needed 12 cookies. Maybe we don't need 24 chocolate chip cookies. We only want 12. That means we'd have to also divide the butter by 2, right? So again, we're just looking at that ratio between products and reactants. Now we could also look at the flour. How much flour do we need for 24 chocolate chip cookies? We need 2¼ cups of flour. So again, we can do the same thing with our molecular formulas that we saw earlier. We can compare the ratios of reactants to products. Now, for example, let's say that we need 2¼ cups of flour, like we saw earlier, to make 24 cookies. But we go to our cupboard and we only have 1½ cups of flour. So we want to figure out how many cookies can we make with only 1.5 cups of flour. So we can set this up mathematically. We can say, okay, I have 1.4 or 5 cups of flour, and the normal ratio is 24 to 2.25. So over here, I simplified everything, so we can cancel our units here and here, cups of flour, and our final unit will be cookies. So this is dimensional analysis again. So all I need to do is multiply 1.5 by 24 and divide that by 2.25 or 2.25. And that should give me 16 cookies. So as long as we have all the other ingredients that we need and we divide that by the appropriate amount, we should end up with 16 cookies. All right, so we can do the same thing with our balanced chemical equations. So this is the equation we balanced earlier between C2H4 and O2, and that produced CO2 and H2O. But we can see the ratio here is 1 to 3 to 2 to 2. So we can set up conversion factors for pretty much anything we want. For example, we could say, okay, there's 2 CO2 molecules that form for every 1 C2H4 molecule. Or maybe we want to compare water and oxygen. We could say, okay, 2 H2O molecules form for every 3 oxygen molecules. You can also compare reactants to each other. So you could say, I need 3 O2 molecules for every 1 C2H4 molecule. And you could also compare the products. You could say 2 H2O molecules form along with 2 CO2 molecules. So we can set up any ratio we need, and depending on what we're solving for, that will go in the numerator. So for example, in the first ratio, we would be solving for CO2. So maybe the question would be, how many CO2 molecules form if we have 4 C2H4 molecules? And then whatever's in the denominator is what we have, and so that's what we're going to cancel in terms of units. So let's do a practice problem using conversion factors. So we're going to use that same equation that we saw on the last slide. And the question is, how many CO2 molecules will form if we start with 10 molecules of O2? So let's break this down a little bit. So we're solving for the amount of CO2 molecules. And we're given 10 molecules of O2. So all we're interested in is CO2 and oxygen. So we can actually ignore the other molecules in this reaction, and we can just focus on what we're solving for and what we're given, which is CO2 and O2. So in the first part, let's write the conversion factor that will help to solve this problem. So I mentioned earlier that what we're solving for should go in the numerator or in the top of our conversion factor. So let's put 2CO2 in the numerator. And what we're given will go in the denominator because we're going to cancel that later. So we'll put 3O2 in the denominator. So again, we're solving for CO2 because the question asks how many CO2 molecules are we forming. And in the denominator, we put what we're canceling because that's what we're given is O2. So now let's calculate the number of CO2 molecules that will form. So I'm going to start by writing out what we were given, which is 10 molecules of O2. So again, that was what we were given. And now we're going to multiply that by the conversion factor that we just wrote down. So 2CO2 over 3O2. So now we can cancel molecules of O2, and that will give us a final unit of CO2 molecules. So all we need to do, we'll multiply across the top, 10 times 2, and we'll divide by the denominator, which is 3. All right, so this should give us 6.7 CO2 molecules. I'm running out of room. All right, so that's not a whole number, but the main thing I wanted to show you is how to set up that conversion factor and then how to use it in an equation so that we can figure out how many CO2 molecules we expect to form if we start with 10 molecules of O2. So again, very similar to our recipe that we saw earlier with the cookies. If we had, let's say, 10 cups of flour, how many cookies could we make? Assuming we had enough of everything else, right? So it's the same exact thing with our molecular formulas. All right, let's do another one. How many C2H4 molecules are needed to produce 16 molecules of CO2? So try this one on your own, and again, it'll be very similar to what we did on the last slide, but we're looking at the other two molecules this time, C2H4 and CO2. So pause the video, try this on your own, and then we'll go over it together. Okay, so again, we're asked about C2H4 molecules. So that is what we're solving for. And we're asked how many of those are needed to produce 16 molecules of CO2. So that's what we're given. So this problem is almost a little bit backwards, right? In this case, we want to produce 16 molecules of CO2, so we need to figure out how many C2H4 molecules we should start with. So if we think about this like the chocolate chip cookie recipe, what if we wanted to make 36 cookies? We would need to work backwards and figure out how much flour we need, how many eggs we need, how much brown sugar we need. So again, same exact thing here, but we're just using molecules instead of ingredients. So let's just focus on C2H4 and CO2. So let's write the conversion factor that will help us solve this problem. So again, we want to put what we're solving for on the top in the numerator. So that's 1 C2H4. And again, that 1 is just coming from the coefficient here. So remember, we don't always list the number 1 in our ratios or our coefficients. So if there isn't a number in front of a molecule, that means there's just one of that molecule. And then we're going to divide that by what we're given. So we want to focus on the CO2, and it looks like there's a ratio of 1 to 2 between C2H4 and CO2. All right, so again, we're solving for C2H4, and we want to cancel CO2. All right, so let's calculate the number of C2H4 molecules that we need. So I'm going to start with what we're given in the problem, which is 16 molecules of CO2. That's what we want to form. So again, that's what we're given. And let's multiply that by our conversion factor, which is 1 C2H4 for every 2 CO2. Okay, so we're going to cancel molecules of CO2, which will just leave us with what we're looking for, C2H4. And let's simplify the math a little bit here. So if we multiply across the top, that's 16 times 1, and we're dividing by 2. And that will give us C2H4. So really it's just 16 divided by 2, right? So that should give us 8 C2H4 molecules. All right, so we figured out that if we want to make 16 molecules of CO2, we need 8 molecules of C2H4 to start. And that makes sense, right? If we look at the ratio between those two molecules, it's 1 to 2. So if we form 2 molecules of CO2 for every 1 molecule of C2H4, it makes sense that if we need 16 molecules of CO2, we're just scaling everything up, right? So that means we need 8 molecules of C2H4. All right, so hopefully that's not too bad. We'll get some more practice in the homework assignments. And then, of course, you can ask me questions if you're unsure of how to set these problems up. But in the next video, we'll dive into types of chemical reactions. So I will see you then.